Hello everyone. This is class number 2 from module 4. So in this section we will be discussing temperature measurement. Instruments used for temperature measurement. We will get introduced to that. We will go through the basic principles, the working and application of those instruments used for measuring temperature. The content of this section is this. We will be starting with the pressure thermometer, then we'll move to another one called resistance temperature detector, or in short called RTD. Okay. Then will move to the thermocouple, which work on Seebeck effect. Then we will study the three laws of thermocouples, then their connection in series and parallel forms. Then we'll introduce the pyrometry, which is one of the techniques for measuring the temperature. Then optical and infrared pyrometers, which works on the principle of pyrometry. So this is the nutshell of today's class. Yeah, the first one, pressure thermometer. Okay. The basic principle is that here when a liquid or vapor, when they are heated, its volume will change, and subsequently its temperature will also, sorry, the pressure will also change. So this is the basic principle of a pressure thermometer. I repeat, when a temperature of liquid or gas is changing, its volume and pressure will also change. Okay, so this is a basic working. Here you have a sensing bulb which senses the temperature in the liquid to be measured. Okay. And this sensing bulb has some it is filled with some uh, liquid, mostly is mercury, because mercury has a good thermal expansion capacity. Now it is connected to the capillary tube, and at the end you have a Bourdon tube. You are already introduced to the Bourdon tube, because it's an instrument which convert some quantity to a displacement. So Bourdon tube will convert the change in pressure to displacement, and this displacement is converted to a linear displacement using linkage, amplified it, and it is presented to the public using the pointer and the temperature scale here. So this is the construction. It has a sensing bulb, capillary tube, and a Bourdon tube. So these are the three basic components. The sensing bulb contains a liquid or gas. The bulb is connected by means of capillary to the Bourdon tube. Okay, it has a capillary and a Bourdon tube at the end. The free end of the Bourdon tube is connected to the linkage, and thereby it is connected to the pointer and the temperature scale. Now, when the temperature of the sensing bulb is changed, when it is come to contact with a hot body, the temperature of the sensing bulb will change, and this change in temperature will change the volume of mercury in it, and subsequently pressure will also change. So this is connected to Bourdon tube, which makes a displacement change at the free end. So this is the free end of your Bourdon tube. So here we will have a displacement, and this displacement is converted to a linear one and amplified using proper linkages, and it is presented using a pointer and temperature scale. So these are the advantages and limitations. Okay. Capillary tube has long as may be used. Okay, the small size of your bulb used to get the highest response. The main advantage is low cost and stable operation, and it has a high accuracy with a maximum of plus or minus 1 degree Celsius accuracy. Now the errors are uh, due to filling fluid and tube. The fluid in the tube, uh, filling the fluid in the tube may have some error, and that's one yield for the limitation. Now it is not suitable for long transmitting capillary tubes, and the filling fluid may give calibration drift. So these are the limitations. Now the next one is the RTD, or the resistance temperature detector. It is also known as resistance thermometer. So here, this one is an electronic device. When temperature changes, resistance of an electric wire will also change. Reverse, vice versa too. When the electric the resistance changes, temperature will also change. So this principle is used in RTD. You can take a wire, and when it is came in contact with a hot body, its temperature will change, and subsequently its resistance will also change. So it is easy to measure the change in resistance. It is very much easy to measure the change in resistance. So you can relate the change in temperature and the change in resistance. So that is the advantage of RTD. And now this is the variation of resistance uh, with the temperature. The relation is given. RT and R naught are the resistance at the temperature T and temperature 0 degrees Celsius. When temperature changes from 0 to some quantity T degrees Celsius, your resistance will also change according to this equation. Okay. The main advantage is that it has high accuracy, and mostly we will using copper, nickel, or platinum as a material of wire. Okay. And the figure shows that resistance change with temperature for the three materials, and from this you can analyze that for platinum, the change in temperature with resistance is varying linearly. Okay. And it says it has approx zero point 0.4 ohms per degree Celsius of temperature variation with it has zero point ohms per degree Celsius of resistance variation with temperature. Okay. Now the next one is your thermocouple. A thermocouple is a device which works on Seebeck effect. Now it has two wires made of different metals, and they will be joined at each ends. Now the one end of your wire will be kept at a lower temperature, which we already know that end is taken as the reference end. So the temperature at this reference end is known for us, and the other end, uh, this will be made in contact with the object whose temperature is to be measured. Now, when these thermocouples came in contact with the hot body, and the other end has cold body, there will be an EMF produced in it, and this is according to the Seebeck effect. And this EMF produced is approximately proportional to the change in temperature. Now, if you can measure the EMF produced, then you can relate it to the temperature change. Now, temperature at one end is known for us, and the other end you can calculate. Okay, so this is a figure. You have two wire. One is wire type A, which is made of one metal, and the wire type B is made of another metal. And these two wires are made in contact with a cold junction whose temperature is known for us. Now the other end is made in contact with the hot body. So an EMF will be produced in the wire, and that can be uh, measured. EMF can be measured, and you can relate this EMF to the change in temperature. Okay. Uh, um, Mostly, the materials used are a combination of antimony and bismuth, or copper and iron, or copper and constant, are the combinations of material used. Now we have three laws of a thermocouple. The first one is the law of homogeneous circuit. Okay. It says that for a thermocouple the two ends will be at different temperature. Say the temperature are T1 and T2 at both ends. Now it says that the EMF produced is dependent only on the temperature at the two ends. Now, if you have different temperature at the intermediates, let it be, but the EMF is unaffected by those temperatures. So that is a statement of law of homogeneous circuit. It simply means the EMF produced in the thermocouple is dependent only on the temperatures at the ends. Okay, so this is a statement. Here you have a T1 and T2 at the two ends. Then at some portion in wire 1 you have a temperature of T3, and some portion in wire 2 you have a temperature of T4. But still, the EMF produced will depend. It's a function of your T1 and T2 only. Now, law of intermediate metals. No, it says that a third metal may be introduced into the thermocouple system without affecting the EMF generated, if and only if the two junctions of the third metal are kept at the same temperature. This law is applicable when you are uh, in when you are came with practical application. For you may need to introduce a measuring device into a thermocouple system, or if sometimes you may need to introduce some you may need to solder somewhere, or you have to weld somewhere. So such type of material additions is possible. Okay, on such cases, you may think this material addition or this instrument addition in a thermocouple will affect the EMF produced. But it is wrong. EMF produced will be safe if the two ends of the metal are at the same temperature. See here, here you have the temperature T3. Here also you have the temperature T3. So the two ends of the added metal is on same temperature. That means the EMF produced is unaffected by the addition of the third material. So here is a statement. Now, the third law, that is called the law of intermediate temperature. It says that when you add the EMF developed in a thermocouple with temperature T1 and T2 with another thermocouple whose temperature is T2 and T3, then the net effect will be the EMF produced in a thermocouple with temperature T1 and T3. Okay. This is just like your law of addition, okay, or just like your zeroth law in thermodynamics. Right. Now the application of this one is um, when you are using thermocouple with a calibration of zero for calibrator for a reference junction of 0 degree, you are using it for a reference junction of 20 degree. If so, then the correction can be done uh, can be done by subtracting the EMF produced by the thermocouple between 0 and 20 degree. Okay. Now, the next topic is the type of connection in a thermocouple. You have a series and parallel connection in thermocouple. Now, when a set of thermocouples are connected in series, it is called a thermopile. But there is no separate for name for thermocouples connected in parallel form. Okay. Now, the two figures demonstrate the same. Okay. The two figures both are the same. Here in figure 1, you have a series of thermocouples. See, the thermocouple 1 is connected to from B to A. The thermocouple 2 is connected from the end of A. Okay, so this like this they are connected in series. The same figure is shown in figure number 2. Here you have a thermocouple from T1 to T2. Okay, and another thermocouple from G1 to T2 again. So a set of thermocouples, say 1, then here you have 2, then here it is 3, here it is 4, here it is 5, etc. A set of thermocouples are connected in series, and the output EMF is measured here. Now in parallel connection, say one end is connected to T4 and the other end is also connected to T4. So intermediate you have an end T3. So the connection is in parallel. Here also EMF is measured. Okay. And you have equation for the net EMF for series and parallel connection. This is given here. So for your exam, you have to draw the figure in any one of this figure. Then you have to write what is a thermocouple in series, what is a thermocouple in parallel. Then you have to mention the name thermopile. You have to write these equations too. Okay. Now, next content is pyrometry. Now, pyrometry, as the definition says, it is a method of measurement of temperature when a surface is emitting temperature radiations. Now, a surface, if a surface is emitting temperature waves, radiations, then you can collect that temperature radiation and you can measure it. So this is a method of measurement of temperature without a physical contact. Okay. And you have two type optical pyrometer and infrared pyrometer. Those are two instruments working on this pyrometer. So simply pyrometry is a science of measuring temperature without having physical contact with the workpiece. Okay. Now this is your optical thermometer. It facilitates a non-contact type of measurement of temperature. Okay. Now the principle is this: matching the brightness of an object to the brightness of a filament which is placed inside the pyrometer. Now here you have an object heated source here. Now the brightness of this heated source has to be matched with the filament inside the lamp. Okay. If there is mismatch, that mismatch is measured as a temperature change. So this is used where we can't have a contact type measurements like when the temperature is very high in furnace or in molten metals where it is technically difficult to have a contact type temperature measurement. So there all you can use optical pyrometers. And the next one is an infrared pyrometers, which is known for you. This one is popular when during this COVID time. Okay, this is used for temperature measurement widely during the COVID time. Okay. Here, an object when it has a temperature greater than the absolute value, it will have atoms moving in a faster manner, and the speed of atoms will be related to the temperature. Okay. So according to the increment in the temperature, the speed of the movement of atoms will also increase. Now, when this atom is moving, they will be emitting infrared waves. Okay. So, like the case in our visible spectrum, we can also detect and measure infrared waves. We have facilities for that. Now, here in our infrared pyrometer, we use a lens for collecting the IR rays. So, these are IR rays emitted by the hot body. We will collect it using a lens, and we will be focusing all the rays to a black body which is kept at the uh, far end of your instrument. Now when all the rays are concentrating on black body, there will be a temperature hike in the black body, and this temperature hike can be measured and it is displayed in digital forms. Okay. So here also it is facilitating a contactless temperature measurement. So a detailed description is given here. That's all about the section, and we'll be back with other topics in 1 or 2 days. Okay. Thank you.